Hi, my name is Ben, and we're going to talk about software engineering today. I'm not sure. Everybody hear me okay? So which way is right, which way is left? Well, there's right. So, this is a software engineering school. Right? Hal's told me there's a software engineering school and there's a computer science school. And if we're going to talk about software engineering, we need to first talk about computer science. We need to make that distinction and separate the two so we understand what the difference is. And there's been a lot of talk about what the difference is between science and engineering. Right? And science comes from the Latin, to know, right? Where we build things, we run experiments to know, to expand what we know. That's what science is all about. And we know that engineering is about building things, right? That engineering, and the word engineer comes from Latin, which is to build. And in fact, in Middle English, they use the word engineer to describe people that would build weapons, mass weapons, siege machines, right? Things that threw big rocks at walls. Engineers. And so, a scientist builds things in order to learn more, and an engineer learns things in order to build. And that's what we're taught. That's what we're taught in school. That's what we're taught in work. That's what we're taught the difference is. Okay? Science and engineering. Why is this important to you? Well, if you're an engineering student, it's important to understand the distinction, how one plays the other. If you're a computer science student, you're probably thinking about getting a job where you need to write software and become a software engineer. It's important to understand. So my thesis is actually going to be that this is totally wrong. So let's get into that. Software engineer we can't talk about without talking about where it was born. And software engineer was really born in 1968. There were two big events in 1968 that brought about the birth of software engineering. One of those events was a NATO conference. A NATO conference happened in Germany, and it was in October of 1968. And at this conference, they talked about the software crisis. And the title of the conference, for the first time ever, was Software Engineering. That was the first time that you could see those words put together, software engineering, 1968. And they talked about crisis. There's a problem in software engineering. There's a problem in writing software. And the problem is that software projects, always run over budget. We spend too much money. Software projects always run over time. We estimate they'll take 6 months, they take a year, they take 2 years. Software projects are hard to manage. And even after you finish the project, sometimes the software doesn't work right. It doesn't follow spec. It's slow. It doesn't work very well. Sometimes you don't ship the software at all. And so there's this big crisis. We call it the software crisis. And the solution to the software crisis was software engineering. We're going to start building software the way we build bridges. Right? So they examined the problem at this conference, and they decided the problem came down to 3 things. Number 1, complexity. Software projects are too complex. And if you need any evidence of that, take some code you wrote, and I know everybody here has written code. Take some of your source code and show it to your mom. Right? Does she think that's, well, unless your mom's a coder, does she think that code looks complex, or does it look simple? It looks complex. At this NATO conference, they talked about that source code, they were writing assembly at the time. Now, COBOL was around, right? Fortran was around, but most software is still written in assembly. In fact, at the time, most software didn't even get sold as software. It was just something that came with the hardware. There was no distinction. It wasn't until 1969 that IBM, for the first time, unbundled or separated software and hardware and sold the software by itself. So until this time, it wasn't even sold by itself. Source code is complex. And if you could get rid of source code, you could get rid of programmers. Ask any CEO, say, Hey, what if you could get rid of your programmers? A smile will appear on his face. Because that's where all the complexity is. That's the hard part, right? The second problem is fallibility, or human error. Remember, because the blue screen of death here? The second big problem is human error. So in theoretical physics, they don't make mistakes. Not many of them. In mathematics, they don't make mistakes, right? But in building software, we make mistakes all the time. We fail all the time. In fact, when we talk about today, it's part of our process to fail. We want to fail. We want to fail and learn from that failure. But that's nothing like the other disciplines. And lastly, they said we suffer from variability. All of our projects are different. Now, this one to me was a real simple, logical error, the way they thought about things. Because again, once they titled the conference Software Engineering, that's our solution to the problem. Once they said software engineering, they started thinking about other kinds of engineering, like industrial engineering and civil engineering. And they thought about building bridges. So I looked at a study in 2009, 24% of all software projects, just in 2009, failed. That's just 5 years ago. 1 in 4 software projects failed to deliver, just did not complete. Imagine if 1 in 4 bridges fell down, right? That would be bad. And so in 1968, they were thinking about this project variability, and they were thinking about, how do we make building software more like building bridges? And the error that we see today, we understand the error very easily. If we look back in time, that they didn't see, is that when you build a bridge and you're in a lab, you make a bunch of models of that bridge and you test it and you break it over and over again until you finally come up with the right blueprint. And you take the blueprint and you give it to the people that build the bridge, and they can build it 100 times. It doesn't fit. And it doesn't fit. Well, to us in software, what's a blueprint? Source code, right? What's the machine that builds the bridge for us in software? It's the compiler. How often does the compiler fail? It never fails. What fails is the blueprint. So they were just thinking wrong. At any rate, they thought if we could fix these 3 things, then we could make software better. Right? And so we propose a new discipline, and it's called software engineering. Blueprints and everything else. And we're going to eliminate and get rid of complexity, fallibility, and variability. We're just going to get rid of it, eliminate that. The second super important thing that happened in 1968 was this. I'm going to play you a clip from a demonstration. Let's see what we can do with this. And I'm just going to play it through and then we're going to talk about it for a second. Nope. This is Engelbart, and this is 1968, and this is in San Francisco, and there are 1,000 people in the audience in a room a little bigger than this, and he's got a computer there overlaid on a screen, he's typing, and at this demonstration in 1968, never before did people see a word processor, never before did they see what he's about to use right here. He doesn't even talk about it. You know what that is? It's a mouse. That's his mouse cursor. First time ever anyone's seen a mouse cursor. Their minds are blown. They don't know what's going on in front of them. He does hypertext, where you click on a word and it takes you to another document. He shows dynamically linked documents, file handles. He copies and pastes. And then they show an overhead. In just a minute, it's going to show you an overhead. And you can see Douglas Engelbart, 1968, right there. There's his mouse, his keyboard, and I don't know what that is. No idea. But it's really cool, isn't it? This is 1968. No one's seen anything like this. This is such an important demonstration. This is such a mind-blowing demonstration that later on they call this the mother of all demos. Very important. Because without this, you don't get the Xerox Palo Alto Research Center. You don't get the Macintosh. You don't get the Apple Lisa or the Apple Mac. You don't get Windows. You don't get anything we use to take for granted today without this. This is a very important demonstration. And I said there were 1,000 people in the audience that day. I'm going to talk about one of those people in particular in just a minute. His name is Alan Kato. Let me get to him in a second. So that was 1968. I told you before that in 1969, IBM split their software and hardware and sold software by itself for the first time. 1969. Before 1969, there was no software industry. It was just a computer industry. In 1969, suddenly there's a software industry. IBM is selling software, and that's important. That sets up the 70s. And remember, we're thinking about complexity, fallibility, and what? And variability, right? So, what did we do in the 70s to eliminate those three things, to kill those three things? This is Alan Kay, super genius. He was in the audience for the mother of all demos. And that thing right there is the Alto. And what Alan Kay did was, he convinced Xerox, he with a couple of friends, and with half of the staff from Douglas Engelbart, to start a new research center, to commercialize the things they had seen in that demo. And they called that the Xerox Palo Alto Research Center, PARC, P-A-R-C. And at the center, they did this, and here's the machine, right? And it's essentially the same thing. He's got a mouse, keyboard, monitor, machine. And this is the first time it's been that compact. In addition to having the mouse and doing all the things that he saw in the Engelbart, he also decided that the programming paradigm, the way that we write software was all wrong. That we were procedural. First do this, then do this, do this. And he had seen the work done on Simula, so he invented Smalltalk, which is the second object-oriented programming language. This guy also invented the overlapped window. And there were a number of other things. This guy invited over whoever he could get in San Francisco to come look at what they did and convince them to adopt the same technologies. And in particular, he invited over this guy. Now, does everybody recognize these two people here? Yeah. Who doesn't know? Who doesn't know who these guys are? This is Steve Jobs and Steve Wozniak. Right? This guy is the hacker's hacker. He's the programmer's programmer. Steve Jobs, the guy that made Apple what it is. So they'd already had the Apple I and the Apple II. And Alan Kay tried to talk this guy, Steve Jobs, into doing Smalltalk, the language that Alan Kay made, as part of their next platform, next computing platform. But this guy didn't care at all about object-oriented anything. What he cared about was that mouse. He was just, mind was blown by how amazing that was. And he mobilized his whole team to write an operating system that had that mouse to drive it instead of a keyboard to drive it, that you could get it to the masses, and everybody could use computers. He would eventually, turn that into the Apple Macintosh, which we all know today. The last person I want to point out from the 70s is this guy. This is Dennis Ritchie. If you've ever learned the language C, right, there's a book called the K&R. And if you learn C, you have to read this book, K&R. Brian Kernighan, Dennis Ritchie. This is Dennis Ritchie, and he invented C. That's important. The other little thing he did was he, along with Ken Thompson, invented Unix. So little things, right? Little things. So how did those things affect complexity, fallibility, and variability? It's not easy to see right now, but object-oriented gave us a level of abstraction. Whereas programmers, we think less about, procedurally telling a computer what to do and more about modeling the things that we want to do, the behaviors. But still, they still had a crisis. Projects were still failing left and right. Enter in the 80s. So how did that set us up for success in the 80s, right? Software engineering was still around, so we must have solved that problem eventually. Well, as it turns out, in the 80s, there was a battle for operating systems. There was a battle for, was it going to be the Apple and their operating system that won, the Macintosh? Which they didn't even make the distinction, this is the OS and this is not the OS. Was it going to be Windows? Was it going to be IBM's OS2? In the end, the winning operating system was the operating system that had the best API for developers, for people like us to write software. Because if you get people to write software for your operating system, then you can have programs that people want to use for their computers. Everybody recognize this guy? This is Bernd Strusse. He loved C as well, just like I do. Only C was missing classes. And so he wrote C with classes. We call that C++ now. This guy invented C++. That's kind of important. That happened in the 80s. This is Windows. This is Windows 1. This was released in 1983. This is actually the reason why I went back to 1968. So my talk was about 1995, because that's when my career really started, 1995. But the reason why I'm here to talk about 1968 in the 70s and 80s is because I started to think about 1995, and I realized that 1995 doesn't make any sense at all unless you talk about 1993. I'll tell you why in just a minute. But 1993 doesn't make any sense unless you know about 1988. 1988 doesn't make any sense unless you know about 1983, which is this. And 1983 doesn't make any sense unless you know about 1968. So that's why we're talking about that. So this was released in 1985, but it was demonstrated, see the copyright? But it was demonstrated in 1983. And at the time, Microsoft was writing software for the Apple, which was still unnamed at the time. And when the Apple engineers went back and told Steve Jobs about Microsoft's new operating system that had a mouse, it was driven by a mouse, Steve Jobs went ballistic. He went crazy mad, super mad. And he said to his people, he said, you better get Bill Gates in my office tomorrow. I want to see him. I want to tell him that he can't do what he's doing. So the next day, Bill Gates shows up to Steve Jobs. Steve Jobs was a bigger guy at the time. And he's all by himself. And it's Bill Gates. Steve Jobs has 10 of his developers around him. He said, what's this I hear about you developing an operating system with a mouse? That's what we're doing. You can't do that. We won't let you write software for our platform anymore. You know, you've seen all of our secrets and how we're doing it. We didn't even know you were doing it. You were doing it in secret. You're going to compete with us. You can't do that. You were stealing us. You were ripping us off. And Bill Gates said, well, Steve, I don't see it that way. Bill Gates said to Steve Jobs, the way I see it is, we both have this rich neighbor called Xerox, right? Xerox Park. And I went in, I broke into Xerox house to steal their TV. I noticed it was already missing because you stole it already. Okay? Xerox invented the idea of the Windows operating system, and Steve Jobs stole it. Right? So how can you be mad at Bill Gates for doing their own? So I told you about the API, the Windows API. The thing that made Windows win in the end was they were developer friendly. When I say developer friendly, I mean this. This is Hello World. I went ahead and went back to the old Windows API and rewrote Hello World for you. You're welcome. This is Hello World. You like that? It's terrible. It's an abomination. They should be ashamed of themselves. But they showed up to the operating system fight with this in their hand as a weapon, right? And everybody else showed up with no weapon. It's like going to war and you've got a stick and no one else has anything, right? Windows at least had the stick. Not very good, but it was something. That was the 80s. Did we solve complexity? Nope. Did we solve fallibility? Nope. Variability? Nope. So we've been in crisis mode since 1968. Projects are still failing left and right. How are we doing in software engineering? We're doing terrible. So the 90s. What is the 90s about? Well, the 90s was about the ascendance of Windows. Windows 1 and it became this hugely popular thing, Windows and networks. We're going to talk about that. But again, how to be thinking about those three things: complexity, fallibility, and variability. Windows got better. Minesweeper. This is Windows 3. It was released in 1990. Raise your hand if you used Windows 3. Oh, am I the only old one here besides Max? Wow. This is Windows 3. So the 90s for us were important because as software engineers we need to be writing for a platform, right? I mean, you could be writing against hardware. I mean, how many people are writing hardware device drivers right now? Nobody, right? We're all writing, the hardware's been abstracted from us. We write for some platform. It could be Apple's platform, it could be the Windows platform, but we don't write for hardware anymore. That's why Windows is important for us. It's an abstraction, right? It's a reduction in what we're concerned about. And that's good for complexity, all right? That's good for getting rid of human error if we have less to deal with, right? Writing device drivers is significantly harder than writing a Hello World app. So, Microsoft at this time, 1990, was still writing IBM OS2 with IBM. It was a partnership, IBM and Microsoft, writing OS2. And OS2 was a superior operating system. Everybody knows OS2 was better than Windows. Okay, you guys are too young to know it, but it was this big deal when I was, 15 or 16 or whatever it was, that OS2 was this great operating system, and Windows was a plaything. If you want to do business, you have to use OS2. Well, Windows 3 was released in 1990. It sold well. It sold over 1 million copies. It took some people at Microsoft by surprise. They were betting on OS2, the business software. They want to get on the desk of every business user. And it caught them by such surprise that Bill Gates and the whole team decided to take their current investment into OS2 and move it into Windows. Take all their developers, the best developers, away from OS2 and put them on Windows. Well, obviously, IBM was thrilled. IBM was mad. They said, "Okay, we're going to do it without you." So, and they get rid of the partnership. And so Microsoft hired this guy. Nobody knows who this is. Maybe. How do you know who this is? Dave Culler. Right, perfect. This is Dave Culler. So in 1988, Microsoft hired Dave Culler. And the reason why they hired Dave Culler was because they had some inkling about Windows 3 being successful. And they wanted Windows to be a real operating system and to really compete with OS2. So they were cheating a little bit. Okay? They said that because of the success in 1990, that's why they decided to do their own serious operating system. They lied. That's okay. I mean, that's business. They hired this guy from Digital, where he wrote VMS, a real operating system. And they said to this guy, "We need you to come in and take over Windows. Bring your best engineers, take over the Windows development, and make it a real operating system that businesses can use." This is Dave Culler. Dave took a look at the Windows code base and said, "No way, this is junk. I'm going to write my own operating system. I'll call it Windows, right? But it's not going to be this code base." And so he started the Windows NT project. Today, when we think of Windows, it's this new code base, not the old code base. It's not Windows 3.1 that moved on to Windows 95. It's the thing that Dave Culler made, which was Windows NT, and eventually became Windows 2000, Windows XP, Windows 7, Windows 8. We won't talk about Windows Vista. Pretend it didn't happen. So, this was a true 32-bit operating system. He said that portability was number one. That there were multiple CPUs, Intel, PowerPC, the i32, the MIPS, the RISC processor. There were tons of instruction sets and processors, and Microsoft didn't know who was going to win, so the operating system had to run on everything, first of all, which turned out to be a pretty good thing, because today you can run Windows on an ARM processor, you can run Windows on an Xbox, you can run Windows on a phone, usually on a processor. But portability was important, as well as reliability. It's a terrible screenshot. Networking was impactful for us as software engineers, because now we had to write software for not just one computer, but computers working together. Now, Novell was really the first one to see and take advantage of this. Again, it's something that came out of that Xerox Palo Alto lab. Bob Metcalf worked in the Palo Alto lab, went on and invented Ethernet there. But no one really took advantage of this and wrote their directory product, directory services product in 1993, taking advantage of the network and how impactful that was. Windows NT responded just 2 years later. It's a 2-year turnaround cycle for Windows NT 3.5.1. This is when I joined Microsoft. Joined Dave Cutler's team, working on Windows. I think the last thing I want to talk about in the 90s was this goofy guy here. Anybody know who this is? Al? James Gosling. He invented Java. Now, whether you prefer C# or Java or some other language, if you write any managed code at all, you need to thank this guy. Because while the concepts weren't new, they weren't commercially viable in a compiler until Java. And in my mind, there's a direct relationship between Java and C#, which is one of my favorite languages. And if you ask Anders Hallsberg, who invented C#, he'll tell you the same thing. So, regardless of your preference, he's important. All right, so we went through the 90s. How are we doing in complexity? We're improving. Right? We're improving. We've got more abstractions, more object-oriented. We have Java coming along. No one's using Smalltalk, but people are starting to use Java. How are we doing on our fallibility, our human errors? We're starting to reduce the scope, right? We have more and more APIs, less and less driver development, hardware. We have more hardware abstraction. How are we doing on our project variability? No change. So, what were the 2000s? This is Windows 2000. That screenshot. This is the product that I last worked on. This was the first Windows NT that had plug and play. Again, getting ourselves away from hardware. As software engineers, it's better for us to be abstract from those problems. And this is also the first version of Windows to have the .NET framework. So if you write any Windows code, you know how important the .NET framework is. It's super, super important. In the early 2000s, the Agile Manifesto was written. You're familiar with the Agile methodology, right? Instead of waterfall for how you develop software. I said before that my team fails. Right? Failure is part of our process. It's part of a learning process. As you're designing a bridge, you need to make a model for your bridge, and you break it, and you break it, and you break it. You find out how much weight you can put on your bridge design before it breaks. Even if you don't want it ever to break, you still keep on putting weight until it breaks, so at least you know when it's going to break. We do the same thing with software. We put heavier and heavier loads on it to see when it will break. Eventually it's going to break. We're going to eventually break it, but we want to know where that is. And when you were developing with a waterfall methodology, the old way of writing software, you didn't plan our failure. Every step had to be successful. It took 10 years for this to catch on, but it's worth noting the Agile Manifesto. Agile wasn't a new idea, it was just dusted off and made new again.
Well, I mentioned one, I would have probably wanted to
Who's this?
This
is Anders Hallsberg.
One, because that would just be one fewer concepts.
This is, I just want you to see how he was being asked, what mistakes did he make in developing C#? That's the question. What do you regret? What's the worst thing about what you did? What do you see with this guy? He's smiling. He was asked what he doesn't like in what he did. Where did you fail? Where did you go wrong? What would you do over if you could? The worst kind of question, actually my favorite interview question of all time. And he's still smiling. He loves what he does. So this is Anders Hallsberg, and he's important because he invented Turbo Pascal, Delphi, J++, C# and TypeScript. So he's important to you. And he's the best developer ever. So here we are. We're in 2000s. We're almost to modern times. What happened to the crisis? Right? Software engineers are still failing. They're still complex. There's still human error. There's still variability. But we stopped talking about it because it just kind of fizzled out. We stopped trying to eliminate those things and just embraced them. Until Vista. Right? Everybody remember Windows Vista? So it was released in 2007. The version of Windows before that was Windows XP, released in Windows in 2001. That's 6 years. This project was so poorly handled, so poorly run, such a terrible project, they actually reset it right in the middle. In 2004, they stopped all development. We're talking 2,000 developers. And they say, stop what you're doing. We're going to reset and start all over again from Windows Server 2003 SP1. Take that source code and start all over again. Stop what you're doing, erase 6 months of work, or almost a year. We're going to start all over again. It's so out of control. Yeah. Software crisis? Heck yeah, we have a software crisis. That brings us to today. This is the decade of the sandbox, in my opinion, so far. It's only been, we're like 5 years in. But, you know, we've stopped concerning ourselves with coding the world, coding security, and the platform, and messaging, and eventing, and logging. And now we have this little sandbox we write code for, right? The app framework, whatever framework that is provided for us. Whether we're doing mobile phone, whether we're doing Windows, or anything else, you know, we play within a sandbox. And certain problems aren't problems anymore. Software distribution used to be a problem. Getting software from one place to another, getting it installed and configured and deployed on 1,000 boxes was this huge problem. And now we don't even think about it. It's just done for us. Right? Sandboxes are good. Sandboxes everywhere. We live now in a box. All of us. I mean, you're writing software, you live in a box. And there's no better symbol than that for that than to look at modern desktop. The modern desktop, there's where you live and you don't get out. That's your sandbox. Well, that's reduction. We're dealing with the problem of fallibility by reducing the scope, making it smaller, being responsible for less. So we changed the world. They promised us flying cars and gave us 140 Fahrenheit. I was told that, but the joke wouldn't fly. So we have email, we have video conferencing, we have changed the world. But what have we done about those three things? Have we, as software engineers, eliminated complexity, human error, fallibility, and variability? No. No, we didn't. What we've actually done is we've embraced those things. We've embraced complexity through abstraction. Right? An object-oriented approach in some cases. We've embraced fallibility with reduction. Right? Sandbox, we play on that sandbox now. Someone else, a specialist, gets to worry about security. A specialist worries about signaling. A specialist worries about each of the little pieces, and you worry about what you're going to bring. And we deal with variability through agile methodology, through iteration. It's okay to fail because we've only got a 3-week sprint to fail in. And we always change our mind and do something else. You're in a 2-year sprint. Failing is bad. You're in a 2-week sprint. It's okay. It's not the end of the world. So, when this defines software engineering today, we stop trying to eliminate those three things, and instead we've embraced them. We learn how to deal with them. So one more thing. As I look at agile methodology and what it's all about, it really all boils down to this. It boils down to, I talk to my users, my customers. I try to understand their problem. I make observations about what they're doing, what problems they're trying to solve. And then I write some code to try to solve that problem. Right? I come up with I think this is going to work for you. And then I test that code to see if it worked. Like right away, right? Sprint review. In agile methodology is a sprint review to test it, to experiment. Did that change work? Did it not work? And then I just repeat that process over and over again until I've got a functioning product, right? That's the agile manifesto. That's the agile methodology. That's how we write software today instead of waterfall. That's the scientific method. Are you computer scientists? Or are you software engineers? The distinction is not necessary. We practice science. We use science as a tool to produce software. We are both scientists and engineers. And that's my talk. Do you have any questions?